Welcome to this comprehensive presentation on integrated rate laws for zero, first, and second order reactions. Differential rate laws tell us how the rate depends on concentration at a single instant. But to predict how concentration actually changes over time, we need integrated rate laws. These are powerful equations derived by solving differential rate laws using calculus. They allow chemists to determine reaction order from experimental data, calculate rate constants, predict concentrations at any future time, and understand half-life behavior. In this presentation, we will derive the integrated rate laws for all three orders, show how to distinguish them graphically, work through quiz questions and detailed problem solutions, and consolidate everything in a comprehensive summary. Let us begin. Before we derive integrated forms, let's recall the differential rate law. For a reaction A, going to products with order n, we write rate equals negative dA over dt equals k times a to the nth power. The value of n, whether 0, 1, or 2, is determined experimentally. It tells us how the rate changes when concentration changes. The integrated rate law is obtained by separating variables and integrating from time 0 to time t. This yields an equation of the form a at time t equals some function of time. The key insight is this. Each order produces a different linear relationship between concentration and time. Zero order gives a versus t as a straight line. First order gives natural log of a versus t as a straight line. And second order gives 1 over a versus t as a straight line. And second order gives 1 over a versus t as a straight line. This is how we experimentally determine the order of a reaction. For a zero-order reaction, the rate is independent of the concentration of the reactant. Rate equals k. The rate constant k has units of molarity per second. Integration yields a at time t equals a initial minus kt. This is a linear equation. A plot of a concentration versus time gives a straight line with slope negative k and intercept a initial. Zero-order kinetics occur when the reaction rate is limited by something other than concentration. For example, many enzyme catalyzed reactions at high substrate concentration exhibit zero-order behavior because the enzyme is saturated. And some light absorption processes also follow zero-order kinetics. The concentration decreases at a constant rate until the reactant is exhausted. The half-life for a zero-order reaction is initial divided by 2k, which is proportional to the initial concentration. For a first-order reaction, the rate is proportional to the concentration of one reactant. Rate equals k times a. Integration using calculus gives the natural log of a at time t divided by a initial equals negative kt. Or equivalently, a at time t equals a initial times e to the negative kt. This exponential decay means the concentration drops by a constant fraction per unit time, not a constant amount. A plot of the natural log of a versus time yields a straight line with slope negative k and intercept the natural log of a initial. The half-life for a first-order reaction is the natural log of 2 divided by k, which is about 0.693 over k. Crucially, the half-life is constant. It does not depend on the initial concentration. This is a hallmark of first-order kinetics. Radioactive decay follows first-order kinetics. Many isomerization reactions and drug decompositions also follow this pattern. The constancy of the half-life is why carbon-14 dating works. The half-life of carbon-14 is always 5,730 years, regardless of how much carbon is present. For a second-order reaction of the type 2A going to products, the rate is proportional to a squared. Rate equals k times a squared. Integration gives 1 over a at time t equals 1 over a initial plus kt. A plot of 1 over a versus time yields a straight line with slope k and intercept 1 over a initial. The half-life depends inversely on concentration. It equals 1 over k times a initial. As the reaction proceeds and concentration decreases, the next half-life gets longer. This is the opposite of first order, where the half-life is constant. For a reaction of type A plus B with different initial concentrations, The integrated form is more complex and involves the difference in initial concentrations inside a logarithmic expression. Second-order kinetics are common in gas phase reactions, many bimolecular reactions in solution, and any reaction where two molecules must collide to react. The half-life is one of the most useful kinetic parameters. It is the time required for the concentration to fall to half its initial value. For zero-order reactions, the half-life equals A initial divided by 2K. Each successive half-life is shorter because less reactant remains. For first-order reactions, the half-life equals the natural log of 2 divided by K, which is 0.693 over K. It is constant regardless of concentration. This is the defining feature of exponential decay. For second-order reactions, the half-life equals 1 over K times A initial. Each successive half-life doubles. It takes twice as long to go from 50% to 25% as it did from 100% to 50%. These differences provide a powerful experimental tool. Simply measure the half-life at different initial concentrations to identify the reaction order. The most reliable method for determining reaction order is the graphical method. Prepare 3 plots of your kinetic data. Plot concentration, A versus time, plot the natural log of A versus time, and plot 1 over A versus time. The plot that gives a straight line reveals the order. If A versus time is linear, the reaction is zero order. If the natural log of A versus time is linear, it is first order. If 1 over A versus time is linear, it is second order. Each order also has a characteristic half-life behavior and specific units for the rate constant K. The graphical method works because the integrated rate laws are linear in the correct coordinates. This approach is robust. Even with experimental scatter, the straightest plot is usually unambiguous. Modern data analysis with regression and R-squared values makes this determination quantitative and precise. Quiz question 1. Which plot gives a straight line for a first-order reaction? Option A, concentration A versus time. Option B, natural log of A versus time. Option C, 1 over A versus time. Option D, 1 over A squared versus time. Take a moment to think about this. Quiz question 2. For a second-order reaction, what happens to the half-life if the initial concentration is doubled? Option A, the half-life doubles. Option B, the half-life is halved. Option C, the half-life remains the same. Option D, the half-life quadruples. Quiz question 3. The half-life of a first-order reaction is 50 seconds. After 150 seconds, what fraction of the original reactant remains? Option A, 1/2. Option B, 1/4. Option C, 1/8. Option D, 1/16. Quiz question 4. What are the units of the rate constant K for a zero-order reaction? Option A, inverse seconds. Option B, inverse molarity, inverse seconds. Option C, molarity per second. Option D, inverse molarity squared per second. Quiz question 5. A reaction has initial concentration 1 molar. After 120 seconds, the concentration is 0.25 molar. If the half-life is constant regardless of the initial concentration, what is the order? Option A, zero order. Option B, first order. Option C, second order. Option D, cannot be determined. Problem 1. First order decay. A first-order reaction has K equals 0.0346 inverse seconds. If the initial concentration is 0.500 molar, calculate three things. Part A, the concentration after 40 seconds. Part B, the time for concentration to reach 0.125 molar. Part C, the half-life. Let's walk through this step by step. For part A, we use the integrated first-order law. At time t equals A, initial times e to the negative kt. Plugging in values, e to the negative 0.0346 times 40 gives e to the negative 1.384, which is 0.250. Multiplying by 0.500 gives 0.125 molar. For part B, we use the logarithmic form. Natural log of 0.125 equals natural log of 0.500 minus 0.0346t. Solving gives t equals 40 seconds. Notice that from 0.500 to 0.125 represents two half-lives, so the half-life is 20 seconds. For part C, T1/2 equals 0.693 divided by 0.0346, which is 20.0 seconds. Let's pause and check our work. Problem 2. Zero-order kinetics. A zero-order decomposition reaction has K equals 0.0080 molar per second. The initial concentration is 0.400 molar. Find Part A, concentration after 30 seconds. Part B, time for complete decomposition. Part C, the half-life. Let's solve. For Part A, the zero-order integrated law is A at time t equals A initial minus kt. Substitute 0.400 minus 0.0080 times 30. That gives 0.400 minus 0.240, which equals 0.160 molar. For part B, complete decomposition means A equals 0. So 0 equals 0.400 minus 0.0080 T. Solving gives T equals 50 seconds. For part C, the half-life for zero order is A initial divided by 2K. 0.400 divided by 2 times 0.0080. That is 0.400 divided by 0.0160, which is 25 seconds. Notice after 25 seconds, concentration is 0.200 molar, exactly half the initial concentration. Problem 3, second-order kinetics. A second-order reaction of type 2A going to products has K equals 0.0250 inverse molarity inverse seconds. Initial concentration is 0.600 molar. Calculate. Part A, concentration after 120 seconds. Part B, the time for concentration to fall to 0.200 molar. Part C, the half-life. Let's solve step by step. For part A, use 1 over A at time t equals 1 over A initial plus kt. 1 over 0.600 is 1.667. Kt is 0.0250 times 120 equals 3.000. Sum equals 4.667 inverse molarity. So A at 120 seconds equals 1 over 4.667, which is 0.214 molar. For part B, set 1 over 0.200 equals 1 over 0.600 plus 0.0250 T. 5.000 equals 1.667 plus 0.0250 T. 3.333 equals 0.0250 T. T equals 133 seconds. For part C, the half-life for a second-order reaction is 1 over K times A initial. That is 1 over 0.0250 times 0.600, which equals 1 over 0.0150, giving 66.7 seconds. Problem 4. Determining order from experimental data. Here are the data for A going to products. At time 0, concentration is 0.800 molar. At 10 seconds, 0.678 molar. At 20 seconds, 0.588 molar. At 30 seconds, 0.519 molar. At 40 seconds, 0.464 molar. Determine the reaction order and calculate K. Let's analyze this. First test, zero order. The concentration decrease per 10 seconds changes from 0.122 to 0.090 to 0.069 to 0.055. These differences are not constant, so not zero order. Next test, first order. The differences in natural log values are roughly negative 0.166, negative 0.142, negative 0.125, and negative 0.112. Not constant. Now test second order. 1 over A, values are 1.250, 1.475, 1.701, 1.927, 2.155. The differences are 0.225, 0.226, 0.226, 0.228. Remarkably constant. This confirms second-order kinetics. The slope K equals the total change in 1 over A over 40 seconds. 0.905 divided by 40 gives 0.0226 inverse molarity per second. Problem 5. Multi-order comparison. Three reactions each start with initial concentration of 1 molar. The zero-order reaction has K equals 0.020 molar per second. The first-order reaction has K equals 0.020 inverse seconds. The second-order reaction has K equals 0.020 inverse molarity per second. Calculate the concentration after 30 seconds for each and compare. For zero order, A at 30 seconds equals 1 minus 0.020 times 30, which equals 1 minus 0.60, giving 0.400 molar. Zero order loses concentration at a constant rate. For first order, A at 30 seconds equals 1 times e to the negative 0.020 times 30, which is e to the negative 0.60, giving 0.549 molar. The exponential decay consumed only 0.451 molar. For second order, 1 over A at 30 seconds equals 1 plus 0.020 times 30, which equals 1.60. So A at 30 seconds equals 1 over 1.60, giving 0.625 molar. Comparing the three, zero order consumed the most at 0.6 molar, first order consumed intermediate at 0.451 molar, and second order consumed the least at 0.375 molar. At high concentrations, second order is slowest because the rate depends on concentration squared. But as concentration drops, second order eventually becomes the fastest. Let us consolidate everything we have learned about integrated rate laws for zero, first, and second order reactions. The differential rate law negative dA over dt equals k times a to the nth power integrates to a different time-dependent equation for each order. Zero order. Concentration at time t equals A initial minus kt. This is linear decay, and the half-life depends on A initial. First order, natural log of A at time t equals natural log of A initial minus kt. This is exponential decay with a constant half-life of 0.693 over k. Second order, 1 over A at time t equals 1 over A initial plus kt. This is reciprocal linear decay, and the half-life is inversely proportional to A initial. The graphical method, plotting A, natural log of A, and 1 over A versus time, is the definitive way to determine reaction order experimentally. The half-life behavior provides a second independent check. Understanding these integrated rate laws is essential for predicting concentrations at any time, designing chemical reactors, determining shelf lives of pharmaceuticals, and understanding radioactive decay. Thank you for studying with us.